How do you teach an idea that feels impossible? That's the big question we're tackling today. We're going to dive into one of the toughest, most notoriously difficult concepts in all of science. It's an idea that has stumped students for generations. But this is really a story about a fascinating study that tried to finally crack the code on how to teach it, and what they discovered was not at all what they expected.
You know that feeling, right? When you're staring at a problem in a textbook, you read the paragraph over and over, and your brain just hurts. It will not click. We've all been there. Well, for a huge number of students, that subject is chemistry. And within chemistry, there's one topic that's kind of like the final boss of confusion.
So what is this beast we're talking about? Well, it's an area of chemistry called stoichiometry.
Yeah, that phrase, the math of chemistry, pretty much nails it. Stoichiometry is all about figuring out how much stuff you're going to get out of a chemical reaction. And right at the very center of all that math is one big, hairy, abstract idea.
The mole. And no, not the little furry animal that digs up your lawn. It's a unit of measurement. But it's so massive and so abstract that for decades it has just completely stumped students and frustrated teachers. I mean, the research is crystal clear on this one. The mole concept is a major roadblock.
And here's the real heart of the problem. Because it's so math-heavy, a lot of teachers just jump straight to the formulas, the algorithms, so students learn how to plug in numbers and get the right answer on a test, but they never actually understand what a mole is. They can do the math, sure, but the actual concept, it's just gone.
So a group of researchers and teachers in South Africa saw this exact problem, and they decided to tackle it head-on. But they didn't just want to create a new lesson plan. No, they wanted a whole new way of thinking about how to teach this thing.
They used a framework called TSPK. And I know, that's a total mouthful, but the idea behind it is actually pretty simple. It's basically a structured way for an expert, like a teacher, to break down all their own deep knowledge and then rebuild it in a way that a beginner can actually grasp.
And this is basically how it works. It shows that great teaching isn't just about what you teach, but how you teach it. First, you have to understand what your students already think they know. Then, you figure out what's absolutely essential versus what's just extra detail. You have to anticipate the roadblocks. Where are they going to get stuck? Then, you find powerful analogies and models to help them. And only then do you build a teaching strategy that's focused on the core idea, not just the math.
Okay, so armed with this framework, they didn't just go work in isolation. They formed a team.
And this part is so crucial. You had a group of experienced teachers and science education experts all getting together in one room to share ideas, to critique each other, and to build something way better than any one of them could have created alone. They call this whole process a learning study.
And their process was this awesome cycle of continuous improvement. They'd all plan a lesson together. Then, one person would go teach it while the others observed. Afterwards, they'd get together and analyze what worked and what totally bombed. Then, they'd revise the lesson based on that feedback and do the whole thing all over again. They actually went through this cycle 4 separate times.
So, after all that work, all that collaboration and refinement, what did this supercharged lesson actually look like?
Well, they built the entire lesson around one single powerful analogy. They said to the students, look, forget about the giant confusing number for a second. Just think of a mole like you think of a dozen. A dozen isn't a thing by itself, right? It's just a word that means 12. Well, a mole is exactly the same. It's just a word for a number. A ridiculously mind-bogglingly huge number, yes, but still just a number.
And here was the genius move. They didn't just talk about it, they made it physical. They had the students weigh a dozen small coins and then weigh a dozen large coins. And boom, you can see the light bulbs go on. They immediately got the core principle. A dozen is always 12. But the mass of that dozen depends completely on what you're counting. A dozen feathers weighs a lot less than a dozen bricks. It's the exact same idea with atoms.
So here's how it all came together in their final lesson plan. They started by using the coins to tackle that classic confusion between amount of things and mass. Then they introduced the dozen analogy by having them weigh those coins. From there, they built a bridge from that concrete idea to the calculations, and finally, they extended the concept to the volume of gases. It was this careful, step-by-step journey from something you can hold in your hand to a very abstract idea.
All right, so this was the moment of truth. After 4 rounds of refinement, with a lesson built by experts, based on a solid theoretical framework, did it actually work? The results were complicated. On the one hand, there was a huge jump in scores for the calculation-based questions.
I mean, the students got much, much better at doing the math.
But, and this is the big twist, on the questions that were designed to test their deep conceptual understanding, their actual grasp of the idea of the mole, there was no significant improvement at all. They could solve the problems, but they still didn't really get it. As you can probably imagine, the team was disappointed. I mean, they had set out specifically to fix the problem of students just learning algorithms without any real understanding, and their own results showed they had unintentionally done the very same thing. But the story does not end there, because what the team learned from this failure was maybe even more valuable than if the lesson had been a runaway success from the start. This is the big question, isn't it? If the main goal wasn't met, was the entire project just a waste of time? Well, the researchers would argue, absolutely not.
They realized a few really key things. First, a single lesson, even a great one, just isn't enough to rewire years of thinking. You need a whole series of lessons. They also realized that, for the teachers, the process of collaborating, planning, and reflecting, that was incredibly powerful professional development in itself.
And what did the students remember? When the researchers interviewed them, they didn't talk about the formulas. They talked about weighing the coins. That hands-on physical activity was a total novelty for them, and it's what stuck. It was a profound reminder that learning has to connect to the real world.
And that leaves us with this final thought. This study set out to improve student scores, and by that one measure, it fell short. But in the process, it improved teacher collaboration, it created a powerful new teaching resource, and it revealed some deep truths about how students learn. So what's the real measure of success? It might just be a much bigger and way more interesting question than we think.